Hi, my name is Dennis Derrickson. I'm a professor at California Polytechnic State University in the Electrical Engineering Department. And in this presentation, I'm going to talk about avalanche and Zener diode noise and measurement with the SSAX broadband noise analysis function. So I hope that you might have seen some videos I created on thermal noise and then shot noise in diodes in forward bias. And what I'll do this time is I'll talk about diodes in reverse bias and look at the shot noise and other noise mechanisms that are present in reverse bias diodes. And I'll also construct a small circuit and measure the shot noise and reverse bias of an example circuit, and I'll use the SSAX broadband baseband input to do that measurement to measure very small amounts of noise. So let's start talking about noise mechanisms in reverse biased diodes. Okay, let's look at the circuit itself here. Let's say we have a diode. There's the anode and cathode, and we're going to put it in reverse bias. In reverse bias, the current actually flows in the opposite direction of the arrow right here. So this is the direction of current in that reverse bias diode. To understand what's happening inside the diode, you need to have a band diagram view of that diode. And so the P side of the diode right here is represented on the left-hand side. We have the valence band and the conduction band and the band gap right here. Here's an ohmic contact that makes contact to the P material here. The P material has lots of dopants in it that produce a large population of holes right here in the valence band. And these holes are the majority carriers. There's lots of them. But also in the p-type material, we have just a few number of electrons right here. There are the minority carriers, and there are the minority carriers because there's so many holes that want to eat up the electrons that depresses the quantity of minority carriers. It's interesting also that these minority carriers, although I showed here fixed, they're constantly recombining with holes, and then new electrons are generating on a regular basis. And so on average, that minority carrier electron may live 10 nanoseconds before it recombines with a hole, and then eventually a new thermally generated electron will be generated. So on average, we'll have a few electrons, but any one particular electron of the minority carrier type will only live maybe about 10 nanoseconds. And the same is true here for the N side. In the N side, we have a large population of electrons that are introduced into the material. They're the majority carriers, and we have just a few, not too many minority carrier holes. The minority carrier hole will not last too long because it's in a sea of electrons. It'll be constantly recombining, but then thermally we'll have more holes being generated on a regular basis. But their population is really suppressed by the large population of electrons right here. Now, this reverse biased, and in the band diagram, you can look at the reverse bias by looking at the difference between the Fermi level in the P and the Fermi level in the N. And the difference in voltage between those two is the reverse bias voltage. The reverse bias voltage produces a large electric field in this direction right here. And so what's going to happen is that if an electron right here is very close to this high field region, so whenever this is a high slope, that means there's a big E field. This vertical axis is electron potential. The horizontal axis is position in the diode. So here the electrons have a lot of potential energy. When they're far away from this high field region, they're just kind of going through recombination and generation all the time. But if they are within one diffusion length of the E field region, then there's a chance that they can get to this high field region before they recombine. The diffusion length of a minority carrier is defined as the square root of the diffusion coefficient, which in silicon would have a value of 25 centimeters squared per second, and the minority carrier lifetime, which we're claiming in this case to be on the order of 10 nanosecond. If you do that calculation, you'll find that the diffusion length is a micron or a few microns right here. So if that electron's within a few microns of this high field region, it's possible it will diffuse to the edge, and then once it gets to the edge, it will have a large electric field forcing it down this avalanche, or like a waterfall almost. And that kind of current is called drift current. When you're moving an electron through an electric field, we call that drift current. So it diffuses over here from the edge, starts on the electric field, and then a drift current forms. And the electron, as it goes down this potential barrier, will convert lots of potential energy into a tremendous amount of kinetic energy right here. And eventually it will fall down and join the big population of electrons right here. Now that can't continue indefinitely, so we're going to take a few electrons off the cathode right here by the external circuit to maintain the steady state population of these electrons in the end material. So these minority carriers going through an E field and accelerating is the cause of the current in a reverse bias diode. And let's look at the bias condition right here. So on this axis, we have the diode voltage right here, and the sense of we view the anode as a positive voltage and the cathode as a negative voltage right here in this reverse bias. So this is a positive forward bias right here, but we're biasing at reverse bias someplace right here. There's not much current flowing, and the only current flowing are these minority carrier electrons falling down this potential hill. Or conversely, we also have holes right here, minority carrier holes. If they're too far away from the junction right here, they'll just recombine and then repopulate by thermal generation means. But if they're close to the edge within one diffusion distance, they will catch this electric field and be accelerated into this population of holes. And then to maintain this population of holes, we'll have to take and add some electrons. Otherwise, we'd have too many holes being built up right here. The mechanism right here of these emission of electrons across the barrier is a form of shot noise. And so we'll use the same shot noise kind of formulas, that the shot noise current is equal to the square root of 2 times the electron charge, 1.6 times 10 to the minus 19th electrons per coulomb, times some reverse bias current right here, which will be very small because we have very few electrons right here available to go on this high E field waterfall. And then multiplied by the bandwidth. So typically these currents are nanoamps or picoamps in reverse bias, and making the actual value of the shot noise very small. So if you had a reverse bias current of these minority carrier electrons of 1 nanoamp and a bandwidth of 1 megahertz, you'd only have 18 picoamps of shot noise. And if you have much less bandwidth than that, you'll have even less thermal noise. So generally, the current in reverse bias is so small that shot noise is oftentimes not an important source of noise in reverse bias diodes if you're just having this small current in this particular bias conditions for the diode. But if you move that bias condition from right here over to the reverse breakdown, there's two kind of reverse breakdowns. There's avalanche breakdown and there's Zener breakdown. But if you biased the diode here, you'll have substantial noise generation and substantial current generation. And so let's look at those cases where we bias the diode far out in reverse bias where it's starting to break down. So I mentioned before, there's two kinds of breakdown, avalanche breakdown and Zener diode breakdown. We'll talk about avalanche breakdown first. So in avalanche breakdown, we have this condition where we put even more voltage between the Fermi levels here. So the waterfall right here is very large. The electric field is very large. And so an electron right here, if it's within 1 diffusion distance of the high E field region, will gain kinetic energy, where potential energy of that electron is converted into kinetic energy. So here we have multiplication, where we have started out with 1 electron, it gains energy, it collides with the lattice, and provides another electron. And although both of those electrons are accelerated again, they could provide 4 electrons. So here we got 1, 2, 4 kind of avalanche multiplication. So one minority carrier produces a whole bunch of electrons into the stack of majority carriers right here. The same thing happens with minority carriers in the N region right here. Holes, if they're within one diffusion length, can be accelerated by the electric field and go through 1,2,4 multiplication. Now it's even worse than that. So if these two holes right here are generated by avalanche multiplication, the generation of that a new electron produces a new hole, and that hole can be accelerated. And when they multiply, they'll produce more electrons. So there's kind of this feedback loop right here. So if both electron generation in the avalanche and a hole generation in the avalanche occur, then we got this feedback mechanism that really just makes the current get very large very quickly. And this whole process is very noisy. So there's two noise mechanisms that happen here. They're both shot noise type, but first there's a multiplication. Here we go 1 to 4. There's a 4 times multiplication of the number of electrons that happen in this avalanche process. So we get a lot more shot noise current. But in addition to that, not every electron will go through a 4 times multiplication. Sometimes they'll go through a 2 times multiplication, times a 4 times, sometimes an 8 time. So the gain of the multiplication is not always the same. And the feedback right here is going to cause the multiplication on the whole side to be highly variable. So we got just a multiplication noise, and we got this feedback excess noise that happens. And so in our shot noise equation, this time we have this constant, which is some number m times n to the n power. M is some multiplication, the average multiplication value. So in this case, it shows a multiplication of 4. But there's also this excess noise factor that takes into account this feedback that can happen that will make the system even noisier. And so these are kind of experimental parameters that you get by taking a measurement and try to fit it to the known formula right here. So we're biased here in avalanche breakdown. We get these multiplication of both electron numbers and hole numbers. And we'll get a large amount of shot noise, very noisy kind of environment. In fact, avalanche noise, as we'll see shortly in the measurement segment of this presentation, avalanche is really a noisy process. If you want to generate a lot of noise, go into avalanche mode, and that is quite a good noise generator. There's another kind of, in this bias right here in reverse breakdown, there's another mechanism which is called Zener noise. And so in Zener noise, there's a different mechanism. So the first thing that happens in a Zener diode is typically you really heavily dope both the p-type and the n-type carriers on both sides. And if you heavily dope the n and p-type, what you get in this region right here is super narrow. That's called the depletion region, depleted of mobile carriers. So for heavy doping, that's really narrow. And so I'm showing right here an electron that's filled, and normally electron in that state in the p material would just be immobile. It can't move anywhere. But the quantum mechanical wave function of this right here has a certain spatial extent. And if the spatial extent of the quantum mechanical probability waveform for the electron can extend through this small barrier, it can just tunnel through and then fall down the electric field right here. So Zener diode mechanisms rely on tunneling. And if you had one tunnel right here, it could also do some multiplication. So the formula for shot noise will be very similar, where we're going to have the shot noise as some square root of, I put this constant Z1, which is a Zener tunneling constant, times 2 times the charge on a carrier, 1.6 times 10 to the minus 19th coulombs per charge carrier, the reverse bias current, the DC value of it, and the bandwidth. So similar formula, but we have this Zener constant, which is a little bit different than the avalanche multiplication constant. But in both cases, we can get multiple electrons that are tunneling across, and they can actually multiply too. So this is also another really large source of noise. Zener diode breakdown. So let's do an experiment and see if we can measure this effect with our SSAX baseband noise input. So here's the circuit I built. I took a 10-volt breakdown diode, which is more an avalanche mechanism breakdown diode. I put a 300 ohm resistor in series with it and attached it to a 15-volt power supply. Then I AC coupled the signal right here to a 50 ohm resistor that's at the input of the SSAX baseband input. This is a very sensitive correlation-based receiver, and I've shown this in my thermal noise and my shot noise presentation, so I won't go through the architecture of this again, but very sensitive input. You can measure very low noise baseband inputs. Here's my circuit. I have a SMA connector that's providing bias to a breakdown reverse bias diode right here. Then I AC couple that to this SMA connector, which is going to go to the baseband input of the SSAX instrument. And here's what I got when I did the measurement. So I have this SSAX and baseband noise measuring noise from a hertz to 10 megahertz at this input right here. And this line here represents the noise as measured by the SSAX. And it goes down to all the way down to very low frequencies. But the measured value I had here was about minus 142 dB volts in a 1 hertz bandwidth. So if we went back to these theories right here, this is an avalanche diode. What value of m to the n do you think we might have in this case? And I looked at that and found that if m to the n was 4, then we'd have minus 156 dB volts. And I think if I try to experimentally match my measured measurement right here to a experimental value for m to the n, I think a 10 fit that well. So if you had a 10, m to the n equal 10, that would describe this level of noise that you'd experience at the output of the avalanche diode into a 50 ohm load, which is the input impedance of this SSAX baseband input. So in this case, the noise is very strong and relatively easy to measure. I have 2 million correlations, but this area represents kind of like the area that you're uncertain about, but there's such a large distance between here and the uncertainty region that this has strong signal to noise ratio and very reliable measurement of that noise level from the avalanche reverse bias diode. So summary, reverse bias diodes have shot noise mechanisms, especially in reverse bias breakdown. There can be very large shot noise generation, both in the Zener mode and the avalanche mode. So here shows an illustration of, these are electrons, minority carrier electrons, and they are falling down the waterfall, which is the large potential barrier between the P and N material. This would be the P material right here, and this would be the N material right here. This water on the bottom would be a large reservoir of electrons, and the electrons are jumping down the waterfall and landing in the majority carrier N material right here. They do some multiplication. I don't show my holes, but this is a very electron-centric version of the shot noise mechanism. And it says, I can generate a lot of shot noise in reverse bias, and that surely is the case. So whenever you have a Zener diode in your circuit, always remember that they are big broadband noise generators. So that is the presentation today, and I'm going to next tell you about diode mechanisms of both thermal noise, shot noise, and something new called 1/f noise in transistors. So stay tuned for that presentation.
It's a true story, the biggest conflict in human history. It's World War II from the front lines. Second World War. That was the I like to spread out the network of boundaries and forces instead of sharing whatever. With their back to the wall, the British mounted law beach evacuation. Yeah, no, perhaps if you think Allied group of integrated speed run was sorted by those by aircraft. Allied hospital ships would be attacked. Drop the neck. There's all. There's all of them. And somebody for all cancer. Matter play, most will. That's go. Really strong, strength, but. Huge, like, big. But it didn't know it was full. September 1500 German aircraft brought down. Insofern war Ludwig dann so groß, dass man diese ganzen Einsätze aufgebrochen hat. Dann über England wurde er Like that. 17-year-old. Here's a figure of fish. Three, 1,000. Or we have single box rates. Now, German balls are worth that British city that you terror and thing. Meanwhile, fascist Italy, the faith that would increase the amount of foreign on all fronts. Everybody good. And the young Europe war spread. And is on a mission to build a so-called new border of Asia. They're already at war. Now, Nazi Germany, fascist Italy, and including Japan have been joined forces at the middle of the alliance. They're known as the Axis powers. That is the company I wrote. But there's one more player present here. So we use the world's largest arm. Those who saw them, they had a think of the ambitious nationalists. Fire, one, then spread gold every corner of the road.